This is David Joyner. I'm a professor of mathematics in the U.S. Naval Academy, and I'm going to show you how to use Sage to do some computations with Fourier Series. Sage is a free mathematics program, open source mathematics program available from SageMath.org. You can download it there. You can also try it online for free. Just get an account on sagenb.org. There's also lots of documentation there, tutorials, video tutorials also. There are email lists you can join if you want to ask questions. Lots of things available about Sage on sagemath.org. I'll be using Sage. In fact, this is a live version of Sage. This document here is called a Sage Notebook worksheet. We're working within what's called the Sage Notebook. It actually is running Sage via a browser, or displaying the Sage output via a browser here. And I'll be posting this worksheet. It's called an SWS file to this web page here. The link is at the bottom of this worksheet, but so you'll see it later, but basically you can see it right there. So it's already been posted on the internet. So if you want to run through this yourself, you can. Then to load the worksheet, you go to File, Load. See right there. Okay, let's start off with a short introduction to Fourier Series. Joseph Fourier was a physicist who was a very strong proponent of using these trigonometric series to solve the heat equation, and was so strongly believed in them that he actually now has them named after him. So Fourier series were named after a physicist, a French physicist named Joseph Fourier. He was also a scientific advisor for Napoleon during the late 1800s, and later became a professor in the French university system in the early 1800s. In 1807, he published a memoir called On the Propagation of Heat in Solid Bodies, which he had been working on for many years. I believe he started working on this in the late 1700s. But that is the book that basically published his solution to the heat equation, and we'll be discussing very briefly that solution using Sage later. But first, some introduction, a quick introduction to Fourier series if you haven't seen them before. I'll use an analogy with Taylor series. Taylor series, as you probably know, are a way of re-expressing a function in terms of a sum or a linear combination of simpler functions, namely powers of x. So for example, if you had e to the x, you might have a hard time computing e to the 1.5 or something, but it wouldn't be too hard to compute 1.5 to various powers. So if you knew the power series expansion or the Taylor expansion of e to the x, then you could get, for example, e to the 1.5. Well, Sage computes Taylor series very easily. There's a method called Taylor, and you can see an illustration right here. If you want just the first four terms, you'll see that Sage tells you that it's 1 plus x squared over 2 plus x cubed over 6. And each of those subsums, these partial sums, 1 plus x plus x squared over 2, and then 1 plus x squared over 2 plus x cubed over 6, those different partial sums give you different approximations to e to the x, to different levels of approximation. You can see here's the e to the x function is this solid blue. This dashed line is 1 plus x. The next line is dot dashed is 1 plus x squared over 2. And then we get this dotted line, which is a better approximation, and that's the all four terms. So you can see if you're going from -2 to 2, then the four terms of the Taylor series give you a pretty good approximation. If you want to go from -3 to 3, you should probably get a few more terms of the Taylor series approximation. But you can use a Taylor series to approximate more complicated functions. We'll use the same idea to introduce Fourier series. Fourier series are not going to be sums of powers of x, but rather sums of trig functions, cosines and sines, like you see here. Now, since cosines and sines are periodic, what we're doing is we're only representing periodic functions as linear combinations of cosines and sines. But if you take a function f of x and you rewrite it as a linear combination of cosines and sines, they're actually your nice formulas for these a_n's and b_n's. There's the so-called Fourier series coefficients. Here they are right here. These Fourier series coefficient formulas actually are due to Dirichlet. I don't believe Fourier knew of these formulas himself. So let's take an example. Look at a function f of x from minus pi to pi, which is piecewise constant. It's -1 from minus pi to 0, 2 from 0 to pi over 2, and 1 from pi over 2 to pi. And let's use Sage to plot that piecewise constant function. Not hard to do that. Sage has a command called piecewise. You can put piecewise defined functions together pretty easily, and you can plot them. There's the plot right there, that blue line plot, solid blue line plot. Also, Sage can compute the a_n's and the b_n's symbolically. Just take n to be a symbolic variable like that, and you do the computation of the integrals, the 1 over L, integral minus L to L, that stuff there. Oops. And you can see the a_n's and the b_n's are computed right there. And now we use Sage to compute the several terms of the Fourier series. This is called a partial sum, when you only take a small number of terms of the Fourier series. And so let's compute the partial sum using Sage and then plot that. If we take the first 6, by mistake I said 5 here, but there are actually 6 terms here, and add them together, you can see you get an approximation to f of x, but it's not a very good approximation. It is trying to hug that curve, but it's doing a pretty bad job. 6 terms don't do a good job here. So let's try more. Here are 13 terms. You do get a better approximation. Still not so good. You can see it's a little bit better here than it is, for example, here, but still pretty bad. So let's take more. This is about 100 terms now. And now it's fairly good. You can actually see it's doing a really good job in the middle there, using red dots instead, because this graph is so good. It's really hard to tell the difference unless you use red dots. But it does have an overshoot where there are these jumps. This overshoot is a common phenomenon for discontinuous functions. Fourier series will do a good job of approximating in the middle where it's nice and continuous, but where there's this jump discontinuity, there's this phenomenon that's called the Gibbs phenomenon, Gibbs. Gibbs was a professor at Yale about 100 years ago or so, and he noticed that by using, actually he computed Fourier series using a mechanical calculator instead of, those are pre-computer days. Now, one of the problems with Fourier series, as I mentioned, is this problem that it doesn't do a good job approximating at these jumps. Now, there is a lot of theory that goes into improving that approximation ability using what are called filters, but to explain that you really need to know something about signal processing, so I'm going to skip that, but I just will notice that using Sage you actually can make the convergence much better. This is using only about 50 terms. You can see it's nice and smooth and there's no overjumps at all using Cesaro filters. Sage has quite a few filters that are implemented. You see Cesaro here, Hahn filters are here, and you can even build your own filters here. Your filter here would be F. So if you want more information, you might want to look into a book on signal processing, and then notice that Sage actually will have some of that implemented for you. Okay, enough of approximations, using Fourier series to do approximations of functions. Let's look at it, see how Fourier series can help us understand the physics of sound. If you look at, for example, the sound of a flute, hopefully you heard that okay. That is a flute playing the note A4. And you can see here, this is Audacity, and it is displaying the actual the actual audio file there. This pattern here, this periodic pattern, is called a waveform. And the question, since that waveform, as you noticed, was nice and periodic, question for us is, can we somehow come up with coefficients an and bn that match those and add them up and use Fourier series to approximate that waveform? So if we let f of t denote that waveform, t now is represents time. If f of t is that waveform of the flute, can we come up with coefficients an and bn so that these add up to give us that waveform? Well, these terms in the Fourier series are actually called harmonics in physics and in music theory. So can we come up with a sequence of these simple harmonics that add up together to give us that waveform of the flute? Well, there's another piece of terminology. The an squared plus bn squared square root is called the amplitude of that nth harmonic. And when you look at, there's various websites that actually tabulate for you the waveforms and the amplitudes. So here's a waveform of a flute, and there are the amplitudes that have been computed. And this function here I came up with really by trial and error, because the amplitudes tell you, this first line here, for example, does tell you what a1 squared plus a2 squared square root is. I'm sorry, a1 squared plus b1 squared square root is, but it doesn't tell you a1 and b1 individually. And likewise, this one will tell you a2 squared plus b2 squared square root, but it doesn't give you a2 and b2 individually. So I did some fiddling by hand and came up with this function, and my feeling is that this does a really good job of approximating this waveform. Now, what is the point here? The point isn't that we can play with sines and cosines and match up patterns, but really the point is that this flute sound actually can be recorded much more condensedly by just looking at these coefficients. These coefficients can be represented by very little data compared to this audio file that recorded that flute sound. So if we want, we can use Fourier series to help us compress and digitally manipulate sounds such as the flute. My challenge to you is to try to do the same thing using the saxophone. And if you want to see the links in more detail, you can just download the worksheet as I said. And by the way, at this website, the worksheet is here, but if you don't want to install Sage and try to look at the worksheet inside Sage, there is also this PDF of the worksheet, so you can just read it using the PDF if you're interested. Okay, that's enough of sound. The next application is to try to evaluate a sum that's denoted by zeta of 2. The sum is the sum of the reciprocals of the squares. Here you see the 1 over 1 to the s, 1 over 2 to the s. What I'm talking about is taking s to be 2. So 1 plus 1 over 2 squared plus 1 over 3 squared and so on. What is that sum? It turns out sums are much more difficult to evaluate than integrals. If this is an integral from 1 to infinity of 1 over x to the s dx, you could evaluate that pretty easily using calculus, but sums are more difficult. And in fact, if you want to try to figure out when this function is 0, for which s is this 0, that is a very famous unsolved problem worth $1 million. And it's sponsored by the Clay Mathematics Institute. They will pay you $1 million if you can come up with a determination of the zeros of zeta of s. I'll state the exact hypothesis a little bit more later, but just need to explain that if you take s here, not to be 2, but any complex number, then the problem is that the sum will not converge unless that complex number s has real part greater than 1. So to make this sum to converge to define this zeta function so that it makes sense for s with real part not just greater than 1, but a larger range of s, we need to look at not the regular sum of the reciprocals, but the alternating sum of the reciprocals. If you do that, it turns out this alternating sum will converge as long as the real part of s is greater than 0. So much wider range of values. The only difference between this expression and this expression is this tiny factor here. It's not too significant. It won't affect, for example, the zeros. So we now know how to define zeta of s as long as the real part of s is greater than 0. And now we can define the Riemann hypothesis. It says that if you have any complex number s, zeta of s is 0. And if that complex number has real part that it is in between 0 and 1, then the Riemann hypothesis says that real part has to be equal to 1/2. And no one knows if that's true or not. It's expected that it is true, but no one knows whether it is or not. It's called the Riemann hypothesis. It's completely unsolved, and is possibly the most famous and difficult mathematics conjecture that is open today. Okay, well, let's move on to trying to evaluate the Riemann zeta function at s equals 2. The trick here is to take the function x squared, but restrict it from -1 to 1, and then extend that periodically with period 2. So you have a parabola going from -1 to 1, and then you're just extending that parabola. So you have a union of parabolas going along the line. Its period is 2. That's our function. We're going to find the Fourier series of that function. So here's the formula for the Fourier series, and the coefficients a(n) and b(n). We talked about the formulas for them earlier. And if you use those formulas and compute a(n) and b(n), you'll get these here, the a(n)s and b(n)s. Plug those into here. All the b(n)s are 0, so there are no sine terms, for example. But this is 2/3. Plug it into there. We get 1/3. F of x is x squared, so we have this. Now take x equals 1. When you take x equals 1, you've got cosine n pi here and cosine n pi here, so you have cosine n pi squared, that's 1. If you take x equals 1 here, you've got a 1 there and a 1/3 here. Put that over there, you get 2/3. So you've got this expression. Now divide by 4 and multiply by pi squared, and you get this. So the sum, 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25 and so on, that sum we know converges to pi squared over 6. Here's a real quick derivation of a(n). The formula for a(n) is here, and you can use Sage to compute those integrals, and you can see it's right there. We've got cosine n pi here, which is 0, and cosine n pi, sine n pi, excuse me, there, and those are 0. So we just recover this formula here. So Sage can be used to do that calculation. Finally, we're moving on to the most difficult application to solve the heat equation using Fourier's method. The heat equation is a partial differential equation, PDE. That means you have a differential equation in a function, u in this case, and we're trying to solve for u. So we have the second derivative of u with respect to x and the first derivative of u with respect to t, and they're supposed to differ only by a constant factor k. This k is a positive constant. It's called the diffusivity constant. And what u of xt is the temperature at the point x on a wire of length L at time t. So here's our wire, this dotted line here. We're going to call this endpoint 0, this endpoint over here L, and x is a point on that wire. This wire is a copper wire. We assume it's maybe plastic coated or something. The idea is that heat cannot escape out the middle of the wire, only out the ends. And this diffusion equation, this heat equation on top, that PDE, that describes the temperature evolution of the wire as T increases. The second equation here describes the initial temperature of the wire. So the temperature at the point x at time t equals 0 is f of x. That's the initial temperature. This says the temperature at the point 0 for all time t is 0. So that endpoint is 0 for all time t. The temperature at the point L for all time t is 0. So that point there has 0 degrees for all time t. So imagine your mom has this magical oven. You can put a wire in it, and this oven will heat that wire in the middle to any temperature you like. And then, but it will also always keep the wire at 0 degrees on both ends. Then she turns the oven off, and this will tell you how that wire cools. That's what the heat equation tells you. Okay, let's see how Fourier solved that. Fourier said the first thing to do is define what he calls the sine series of f of x. F of x is defined from 0 to L. So what we do is we take f of x and we create an odd function from f of x that's defined from minus L to L. To get an odd function from minus L to L out of f of x, we take our function f of x, graph it from 0 to L, flip that graph about the y-axis, and then flip that graph over the x-axis. Now you have a graph that's going from minus L to L, and it's odd. When you take its Fourier series, you will have no cosine terms, turns out, only sine terms, and that's why it's called a sine series. I denote this by SS for sine series of f. So this expression right here is the sine series. The bn's are given by this formula here, turns out. And Fourier's formula for the solution to the heat equation is this expression right here. It says you take this sine series here and tack on to each of those sine terms an exponential. The exponential is e to the minus k. K is the diffusivity constant in the PDE. Then you take the coefficient of x inside the sine, you square it, and you multiply by t. That's Fourier's formula for the solution. It was a real quick, very quick, 10-second explanation of why Fourier's formula works. First, you take the heat equation with the initial temperature and the boundary conditions, and you replace f of x by its sine series. That's what that is. Now, superposition says if you can solve this problem here with each of the individual terms, there are an infinite number of them, n equals 1, n equals 2, and so on, solve them all and add them together, you'll get the solution to this. So superposition allows us to reduce this problem down to solving all these problems for each n. Now, separation of variables says what we do is we only look for the solutions u of xt, which are a function of x, times a function of t. Let's call it x of x and t of t. We don't know what x of x is. We don't know what t of t is. To find them, what we do is we plug that product into the PDE. We try to separate variables. In other words, all the x's on one side, t's on the other side. Now you have a separated equation. They have to be equal to a constant, and that allows you to create two ODEs for x of x, one for x of x and one for t of t. Solve them and then use these conditions here to get more information on the form of those solutions, and you will get x of x, t of t equals to this expression. And so that's the solution. That's the individual term, and then you add them up using superposition. So that's a 15-second explanation of why Fourier's formula works for the 0n's case. Let's do an example. Here's our initial temperature. Our wire is length pi. Temperature is -1 from 0 to pi over 2, and then 2 from pi over 2 to pi. L here is pi, as I said, that's the length of the wire. The formula that we had up there for Bn, right there, tells us that Bn is this expression here. This only depends on n here. Just plug in various values of n, you'll get various coefficients. Take n equals 1, you get this. Take n equals 2, you get that coefficient. N equals 3, you get this coefficient, and so on. So the first three terms of the Fourier series are just these expressions right here. You can compute as many as you want in Sage. There's a method called sine series coefficient. It'll compute the nth sine series coefficient. And here what we've done is we've had Sage compute the first 50 coefficients and then add them up and then plot them. So here's our function, f of x. That's the solid blue line. And then we plot this periodic sine series. It's a periodic function with period 2 pi. It goes from minus pi to pi. There's the period right here. Minus pi starts here, pi goes to here. So that's our period. If you want more, you take that block from minus pi to pi and you copy it over here. You take that block from minus pi to pi and you copy it over here, and you see you get the entire graph of the sine series if you really wanted it. We only need this part of the sine series from here to here, though. And now we use Fourier's formula for the solution, this one right here. Notice we're going to have to take e to the minus k times this coefficient of x, and we square it and multiply by t. Now, the formula that we're using in our problem here has k equals 1. Okay, so we're going to take e to the minus k with k equals 1. We take the coefficient of x, we square it, multiply by t. So that's the exponential factor right there that that Fourier said that we should use. We're going to take the first 50 terms that we already computed, add them up with these extra exponential factors, then plot that for various values of t. When t equals 1, we have this plot right here. That's the sine series itself, for the first 50 terms actually. T equals 1. Or rather, t equals 0 is that original. That's the initial temperature. Here's t equals 1 over 20. You can see it's cooled down substantially already, just in 1/20th of a second. That. And then t equals 1/10 is that next smallest curve. And then t equals 1/5. As you know, that because of Fourier's formula, this temperature is decreasing exponentially rapidly. You can see it in the graph, and it also is kind of intuitive, makes intuitive sense it'll cool off. All right, so that's the end. Those are a few ways you can use Sage to illustrate the use of Fourier series.